of the reasons why radar resolution was a challenge for early scientists because the resolution of radars was really very low. This was because of the fundamental constraints in physics and engineering. One of the key factors in determining this is the angular resolution, which is given by the equation. Here, lambda is the wavelength of the radar signal and d is the diameter of the antenna or the mirror. Now, when we are talking about optical remote sensing, this operates on visible wavelength, which are at a nanometer scale. So therefore, the aperture size that is needed will be very low. However, when we talk about microwaves, they do not operate on nanometer levels. They operate in the range of 1 millimeter to 1 meter, which is many more times bigger. So in this equation here, the lambda will increase by a very big number, and correspondingly the diameter of the antenna should also increase to give a comparable angular resolution. However, it is very difficult to make such a big antenna, and that too sending in the space and operating without any trouble. Because to maintain the high resolution as in optical cameras, the antenna needs to be at least several kilometers in size. Is nearly impractical due to its size, weight and structural challenges. Moreover, the antenna must survive the intense vibrations during its launch and then function autonomously in space. So, as a result, the first radar imaging satellites of the 1980s had low resolution because their antennas were very limited in size. While radar could very well see through the clouds and operate at night, the images were much blurrier when compared to optical systems. The physics demanded a very large antenna, but engineering and logistical constraints made it impossible to build one at the required scale. You can see through this diagram the size of antenna that is required with respect to the wavelength. Now, this led to the need for a completely different approach to improve radar imaging without physically increasing the antenna size. I think you have understood the constraints under which we were working that time. That antenna sizes could not be increased after a certain extent, but the resolution of the images needed to be improved. So this is where synthetic aperture radar comes into the picture. So what we do in this is, instead of constructing an 100 kilometer wide antenna, engineers discovered a revolutionary technique. That is, they could use a much smaller antenna and record data continuously as the satellite moves along its orbit. And then by combining the signals received at different positions, they effectively created a virtual or synthetic antenna which can achieve almost the same resolution as a physically massive one. This technique is known as the synthetic aperture radar because here the aperture size is created synthetically. It processes all the recorded radar pulses only after the satellite has traveled a distance equal to the original large antenna's size. And by doing this, SAR achieves high resolution imaging while keeping the actual antenna compact and practical for space missions. Interestingly, this idea of creating a virtual mega antenna is not just limited to satellites. On Earth also, we can combine multiple smaller antennas and form a much larger one. This is exactly how the astronomers captured the first image of a black hole in 2019 using a network of radio telescopes across the globe to act as a planet-sized antenna. This is engineering at its best. Also, because the satellites in the lower Earth orbit travel at approximately 7 kilometers per second. This means that if you want to create an antenna of, let's say, 100 kilometers in size, this would typically take it only 15 seconds to create a high resolution image. And here is the craziest part of all these things, that now with this technology, the resolution of our image will be completely independent up to a certain extent from how far away the antenna is and what is the distance between the objects and the antenna that we want to capture the image of. So that's why the radar technology is not just limited to Earth. We have also bounced radar pulses off the moon and mapped its surface with an incredibly 70 centimeters resolution. This is remarkable. So how does a radar create an image? First, a microwave signal is sent out of the radar in all directions, and then when it encounters an obstruction or a target, the incident wave is reflected back in a certain intensity. This is then recorded and the time elapsed is calculated. However, there is a problem in this because we cannot tell the direction in which this object is located. And to solve this, we can define the direction of the antenna, and then we can clearly tell what is the time delay between the waves and the direction in which it is located. So now the question is, how does a radar create an image? Is it just about measuring the time delay between sending a microwave and then receiving a scattered microwave? Actually, the real image formation involves much more complexity. Let us break it one by one. So we can divide the key parameters that influence a image that is created by a radar into three categories. The first can be a radar characteristic, the second can be a surface characteristic, and the third can be the image formation parameter. Now these three factors are not defined somewhere, neither exhaustive. It can contain many more things, but just for the sake of bringing everything at the same table, I have done this characterization. So let's first start with the radar characteristic. So the radar characteristics ideally consists of three things, that is the wavelength or the frequency of the radar, then the angle of incidence, and then the third is the polarization. So let's first talk about the wavelength. So radar operates in different wavelengths, X band, C band, L band. So here we are talking about that. We will learn more about this wavelength and frequency of a radar or a microwave in the coming lectures. Then the second is the incidence angle. It is the angle at which the radar wave hits the surface. This also we will cover in detail in the coming lectures. Here we are just giving a glimpse of what is there in each of the categories. Then the third is the polarization. Radars, if you have ever used radar data, you might have seen the terms HH, HV, VH, VV. These corresponds because the radar waves can be transmitted and received in horizontal or vertical orientations. Okay, so what is it and how does it works? We will see it in the polarization lecture. So this was all about the various characteristics in a radar that can influence what kind of image is being generated. Then there can be surface characteristics, that what kind of surface you are looking at. Under the surface characteristics, there can be two parameters. The first is the dielectric constant. This determines how much of the radar signal reflects or penetrates the surface on which it is focused on. Again, needless to say, this also we will learn in very much detail in the next lecture. Then the next is surface roughness, the size of the surface irregularities which is compared to the radar wavelength. Either the radar wavelength is greater than the size of the surface irregularity, or it is comparable to it, or lesser than it, right? Then the third category is the image formation. So here we will see what is amplitude and phase of the signal, and that is the data which we generally receive from the radar, and what does it measures. Then what is the complex number in which the data is reported. Then we will see the azimuth resolution and the range resolution. Then we will briefly learn about the backscatter intensity and speckle.